Listen-only mode.
Well, good morning, everyone. Hope everyone is doing well today. Just wanted to let you know we're going to be starting here in a few minutes. This is Kevin Cope. I will be the presenter, but just again wanted to say hello to everyone out there and let them know we will be starting here shortly. Make sure that we get folks that are coming in a bit late. So again, thank you for being here, but we'll be starting here in a few minutes. Thanks.
Well, let's go ahead and get started then. It is 8 o'clock. Hi, everybody. My name is Brian Leota. I'm the marketing director for the water additives business for North America. Brenntag is very pleased to present this webinar today on antiscalants, and hopefully everyone who wanted to participate is here and ready to go or in the process of logging on. This event is one of several webinars that Brenntag plans to present. We want to bring knowledge to our customers and help them improve the quality of service that they bring to theirs. In an effort to continuously improve these customer-facing programs, we're going to encourage feedback from the participants on how well we did today, the relevance and depth of the information covered, as well as suggestions for future programming. Kevin already introduced himself a bit, but I'm going to give more detail. I want to introduce him as our presenter today. A little background on him: he started his career at Petrolite, where he focused on wastewater treatment, oil demulsification, and oil processing chemicals. And later in his career, he joined Dearborn Chemical as a senior wastewater specialist, where he was responsible for marketing, training, and technical support of the Eastern U.S. sales force. He eventually joined Calgon Corporation as a senior sales engineer, focusing on cooling water and boiler water, and eventually managed their technical training program. Most recently, Kevin was with Chimera and held roles in product management and business development. Drawing on his years of practical experience with cooling tower and boiler applications, Kevin developed a deep understanding of antiscalant technology in its many forms. At Brenntag, these days, Kevin's an applications specialist. He focuses on our customers, delivering technical knowledge in support of our water additives business, and he also helps develop a product portfolio, which we build solely around the needs of our customers. Kevin resides in Pittsburgh, Pennsylvania, with his wife, Ruth. We're going to attempt to save some time at the end of today's program for some Q&A. In the event you have some questions we don't get to because of time, Kevin will provide his contact information so you can email him with your question. Also, a PDF version of today's presentation will be made available to the participants on request. So we're very pleased to have Kevin present today's topic, anti-scaling technology. Kevin, take it away.
Well, Brian, thank you very much. I, again, appreciate everyone that's attending and look forward, if there are any questions, answering your questions either after the end or via email. Our presentation today, as Brian said, is on anti-scalants. I will make one comment. Where I'm at, Brian, it is 11, not 8 a.m., so for all those folks in different time zones, welcome at whatever time it is where you're at. Today we're going to be taught, this is the agenda that I will be following today: definitions, applications, anti-scalant types, scale prevention mechanisms, market trends, and market observations. Under definition, to define scale, waterborne contaminants. They form insoluble particulates in bulk water. They adhere then to surfaces, causing problems. Calcium carbonate, calcium sulfate are just some of the examples of things we call scales. Deposit, on the other hand, is an airborne or waterborne contaminant. Solids that are carried into the water either through dust, wind, through a cooling tower, or solids coming in from a river or a lake, or biological materials. When I was with Calgon, when I first started putting this together, I actually lost the slide. I apologize. I actually lost the slide here, and my apologies. When I was with Calgon, we used the term from describing scale. In other words, it is material that comes from the water. It is things like calcium that will precipitate out of the water, coming from the water. Whereas a deposit is something that we consider coming into the water. Brian, if you excuse me for 1 second, something is a little off on this presentation. I'm going to escape. And I very much apologize for this. This is a slide I did want to make sure that I had brought up the next two. And folks, I very much apologize. I don't know what was going on. When I first started to put this presentation together, I thought of it kind of as a crossword puzzle. And when I looked at all the acronyms that we have in our industry, HEDP, PAA, AMP, really kind of, again, we'll hear use a lot of acronyms during our presentation today. But after I thought about it a little longer, it actually made more sense to me to think of these as children's building blocks. And as we put these chemistries together to work on different types of waters, it really came to me as more like building blocks. And what people will do, will take these building blocks and put them together in some kind of a form to create a product that will do many different things: prevent scale, reduce corrosion, prevent deposit or minimize deposits. So I really kind of thought of these more along the lines of a building block rather than a crossword puzzle. So again, we kind of did these already, the scale and definition on scale, and also on deposit. But again, back to my Calgon days, this has always been very, very helpful to me to think through this, that scale comes from the water, whereas a deposit comes into the water. Again, from being scale into being deposit. I will say, however, oftentimes these are used back and forth, at scale called deposit and vice versa, but just for an understanding. And then also, whenever we're looking at this market, we also need to consider corrosion as being something that needs to be addressed when looking at any kind of scale inhibition. The objectives are to prevent scale formation and from deposit from forming. Why? Well, to ensure good heat transfer and prevent flow restrictions. And how this is done is via threshold inhibition, crystal modification, dispersion, and chelation. This is a chart that I like to show, and basically what it shows is what a small amount of scale and how it can affect heat transfer in the system. If you look on the very bottom, just a small amount of silica scale can greatly reduce the ability for let's say a heat exchanger to exchange heat. Whereas calcium sulfate, calcium carbonate, all these other components, how they also restrict heat transfer. I always thought this was a good visualization to show the importance of a good scale prevention program. Some of the applications that we see in the market, variety of different things, cooling water, boiler water, reverse osmosis. The one I was always struck with was the detergent and cleaners. As many of you may know, I have a very strong water treatment background, but during my time working with the anti-scalants, how often the discussion around detergents and cleaners were to come up during working with different water treaters. But again, a variety of different applications, mining, storage, stabilization, just to name a few of some of the applications that we see. The type of chemistries we will be discussing today are phosphates, chelants, organic polymers, and phosphonates. Some of the mechanisms that are used to prevent scale or threshold inhibition, crystal modification, dispersion, and also chelation. Let's start out by first discussing threshold inhibition. As scale is formed, it's very much like back to the children's building blocks, as they are put one right after another. I like to think of the threshold inhibition being maybe a little bit of wax paper put in between those blocks to prevent that structure from forming and from building. And that is what is called threshold inhibition. At the moment that a crystal starts to form, these chemistries will tend to disrupt that formation and prevent that formation from occurring. Crystal modification, although very similar, is basically as that crystal does begin to form, what crystal modification means is we start to disrupt the formation of the crystal. I think these are very, very good pictures. The picture on the left clearly shows some well-formed crystals. I believe these are calcium sulfate crystals, but very, very well-formed crystals. However, the slide on the right clearly shows the disruption that occurs with these particles that prevent them from really getting a good hard structure. So again, crystal modification is allowing the crystal to form, but yet disrupting it so it's not as strong or as adherent as it was untreated. Now, dispersion, many of you may know that have a wastewater background, and dispersion is just kind of the opposite of coagulation. If you look on the left, the slide with the picture of the little cutout with the particles with the negative charges, in coagulation, what we do is we add a cationic polymer to this, and that neutralizes these charges, allowing these particles to become larger and thereby settling out much faster. However, in the cooling water boiler and in the anti-scalant market, we're doing just the opposite. We are adding a negatively charged product that basically disperses these particles even more, preventing them from settling out. And so I always think of dispersion as being just the opposite of coagulation. Dispersion adding a negatively charged particles to disperse as opposed to a coagulant being fed to neutralize and thereby making particles larger for better settling. This is a slide I had from many years ago. Crude oil and water on the left, a small amount of dispersant in the center, and then a larger amount on the right. And you can clearly see how the particles are now dispersed throughout the water, and basically a form of dispersion. For an example, beg your pardon, of dispersion. We did recently a webinar on chelation, and during that part of that time, I was struggling with finding a good definition for chelation. And I went to the book by Colin Frame that I use quite often, and I know Colin very well, and found his definition of chelation to be extremely good. Organic compounds having the ability to take metal ions in water and produce a soluble complex. The best definition I've heard of chelation or chelants. I always thought of a chelant, though, as something like a crab or a lobster. Chelation coming from the Latin word for pincers, but a chelant grabbing a hold of the calcium in the water, or in the case of metals, holding those metals in solution and preventing them from coming out. So, little visual that I've always used over the years, along with Colin's excellent definition of chelation. Again, these are the types of products we'll be talking about: phosphates, chelants, organic polymers, and phosphonates. Phosphates. There basically are two forms: polyphosphates and orthophosphates. Phosphates will tend to sequester metals. They do provide corrosion control. They will prevent scale. They have the ability to remove deposits, and are primarily used in drinking water systems to prevent corrosion. Chelants come in many forms. These are just some of them. The list I have is like 3 pages long, but the real key ones are EDTA, beg your pardon, and NTA. Also citric acid, EDTA oftentimes used in boiler treatments. These are just some of the chelants that are available on the market to prevent scale. Chelants will also sequester minerals. They provide scale and corrosion removal properties. They can be effective cleaners and can be effective boiler treatments. Organic polymers. Here comes the acronyms. We find that in this market, quite a bit of acronyms are used: PAA, HPMA, PASA, PESA. I find that it's the way my mind works, I think of many of the acronyms and then try to remember the names of each one of the chemistries, but for the most part, the acronyms are what is primarily used throughout the marketplace. This next slide basically talks about the forms of organic polymers. We have homopolymers, copolymers, terpolymers, quad polymers, and I guess if we continue throughout history, we'll eventually come up with infinity polymers as we, as an industry, keep adding and adding components and making more and more and more products with the different backbones that we have. Polyacrylates are basically a homopolymer. Various molecular weights are available. They are excellent for suspended solids dispersion. They're good general purpose scale inhibitors, good for calcium carbonate and sulfate. They're fair on barium sulfate and fair on calcium chloride, and they tend to work at an LSI below 1.5. Polymethacrylates, PMAA, again, various molecular weights and pH is available. General purpose, a good general purpose scale inhibitor. They're very good for calcium phosphates. That's why they were oftentimes used in many of the old phosphate polymer programs. Good for transportation of iron. Oftentimes, again, used in boiler formulas, and also are effective at less than an LSI of 1.5. Polymaleics, HPMAs. Various pHs are available, although molecular weight tends to be the same with all products. They're excellent for calcium carbonate and sulfate, very good for dispersion. They're much more iron tolerant than PAAs. They're excellent under stress conditions, and you can see that a little wider range on an LSI, 1 to 2.0. PCA, low phosphorus containing material, suspended solids dispersed, good for suspended solids dispersion, and calcium sulfate inhibitor under high stress conditions. Don't have a manufacturing background, but from what I understand, this is a polyacrylate manufacturing process with the termination used by a phosphorus containing material. PACA and PESA, these are considered biodegradable products, effective on calcium carbonate, sulfates, and phosphates. There is some corrosion control associated with these products, and PESA, and we'll talk a little bit later about calcium oxalate, has been found to be effective on calcium oxalates. So back to the slide, homopolymers, copolymers, and terpolymers. And during my time as training manager, this has always been an area of kind of struggle to really understand by folks coming into the industry. A homopolymer is basically a single component product, whereas a copolymer, like it says, is a two-component product. Can be two different components, can be two like components, can have different ratios. What I mean by two like components, I have seen products that are simply PAAs, polyacrylic acids, but at different molecular weights in the same product line, or excuse me, same product. And likewise, terpolymers are three components, could be three different ratios of different likes or different types of chemistries. So I put this slide together to purely kind of finalize the understanding of copolymers and terpolymers. So if you had one specific product in a drum, say a polyacrylate, that would be known as a homopolymer. The whole polymer is of a product, pH of 7, molecular weight of 2,000. However, if you were to blend that product and put, again, like we talked about earlier, two different molecular weights of the same polyacrylate chemistry, you would be creating a copolymer. Conversely, you could make that same copolymer with a different ratio. One of the more common ratios in our industry is what's called an AA-AMPS copolymer. There's a 60-40 percent version and an 80-20% version of the same copolymer. Although both function very, very differently, they would both still be considered a copolymer. And again, putting in a different chemistry altogether and creating the same copolymer, or creating a copolymer. And then just to finish everything out, a terpolymer would be a combination of three different materials. Copolymers, again, a blend of two different or like chemistries. They are the second generation organic polymers. There are numerous copolymers available. The synergistic effect of putting the two products together can really help improve the performance of each individual component, and they can yield a wide range of scale inhibitions. Again, they're effective over a wider LSI range. Numerous applications can include a variety of different things: magnesium silicate, barium sulfate, calcium oxalate, struvite control. We'll go through struvite a bit later, and others. Some of the more commonly used components in copolymers can include polyacrylates, maleics, sulfonated styrene, acrylamides, and others. Again, terpolymers are a blend of 3 different components, like or dissimilar products in different ratios. Again, next generation of organic polymers. There are several terpolymers available. I do see in the market there are fewer terpolymers available than copolymers. That's just a personal observation. Again, you do see the synergistic effect between the components, improving the components of each individual component. And they can yield a treatment over a wider range of scales. Again, effective over a wider LSI. Numerous applications can include a variety of different things. They tend to be excellent in high stress applications, high heat applications, silica control, and a variety of different applications. The terpolymers are finding to be very effective. Some of the more common copolymer or terpolymer additives, polyacrylates, you'll see basically the same players as in copolymers. With one exception, I do see much more often proprietary components found in the terpolymers rather than in the copolymers. Now let's move on to phosphonates. Again, regular cornucopia of acronyms coming at you right now. ATMP, HEDP. HEDP probably being the most common in this industry, in this market, this product line for scale inhibition, PBTC, and PAPM. ATMP, low-cost phosphonate, good general purpose scale inhibitor, but it is vulnerable to chlorine breakdown, which can possibly yield calcium phosphate scale. And it can work as a corrosion inhibitor when enhanced or blended with HEDP. HEDP, excellent calcium carbonate inhibitor, and it works under a higher stress condition than ATMP. It's good inhibition for calcium fluoride, more resistant to chlorine than ATMP, and can also give corrosion control when blended with ATMP. Going back to that calcium fluoride comment, a lot of experience with the inhibition of calcium fluoride in the steel industry. When a continuous caster, when the molten steel is poured into what's called the mold, they are typically packed with a high fluoride containing material, which then gets on the outside of the steel. And then as the slab is put through the spray section, that fluoride is washed off and can react with the calcium, creating potential for calcium fluoride scale throughout the system. And found that HEDP did an excellent job at preventing calcium fluoride scale throughout the steel industry in a variety of different casters. A little surprised to learn about the fluoride in the casters was something a little bit surprising when I first got involved in it. PBTC is a new not a new product, but a product that's really excellent for high hardness and high stress. It's excellent at high alkalinity. It does perform well in the presence of chlorine and bromine. Excellent for it's a good zinc stabilizer. Also can be an effective and good chelant. PAPM is another high-stress product. A lot of experience with this material. Excellent scale inhibition for calcium carbonate, sulfate, and phosphate under high-stress conditions. Effective over a 100 to 300 calcite saturation. Can inhibit formation of scale from silica. It's stabilized on many of the metal ions. However, it is less effective in low hardness applications below about 100 times calcite saturation. DTE DET PMP, excellent for barium sulfate inhibitor. It's a very, very effective sequestrant. And HMD TMP, excellent for calcium sulfate in high alkalinity applications. So if we were to look at each one of the individual type families, you have the organic polymers. They tend to be scale-specific control. They control deposit very well. They give little to no corrosion inhibition. And the blending of products can increase their effectiveness. In the case of phosphonates, excellent calcium scale inhibition. They give corrosion control. They do, however, little for total suspended solids control, and much like the organic polymers, blending can improve their effectiveness. Phosphates can control scale and deposit. They do function very well as corrosion inhibitors and are primarily used in the municipal drinking water systems. And in chelins, scale and deposit control, they can be a very effective cleaners and can be effective boiler treatments. I'd like to move into some of the market trends and what we see within the market. First is water reuse, with many demands by our government on reusing water. Many parts of our country are being required to increase the number of cycles they use, shutting down once-through systems. So we're starting to see water reuse as really being a big push within our country. Also, that's creating higher stress situations, higher LSI, and higher calcium or calcite saturations. So it's a very, very growing market with our industry of water reuse. Interestingly, where the water reuse is occurring is really where we see the most silica in the naturally occurring water. So we're starting to see higher and higher and higher concentrations of silica, and we're looking at new and better silica control programs are being used and also evaluated right now to increase the amount of silica we can hold up in systems. Also, the geothermal market is an industry with major concerns on silica scale. This here is a map basically showing geographically where we see a lot of the problems with silica, primarily in the Southwest. I will also note that most of Mexico, northern Mexico and coastal Mexico is having quite a bit of problems with silica scale, as is Florida and along the East Coast from the Carolinas down to Florida. Struvite is a combination of magnesium, ammonium and phosphate. It's primarily in the municipal industry. It's causing problems with water lines, mostly the municipal wastewater industry, causing problems with water lines, belts, centrifuges, really scaling up on equipment and causing major problems. Likewise, with the increase in the water reuse and looking for new sources of water, we're seeing an increase in barium sulfate and strontium scales because of the higher cycles. Excuse me. We're starting to see much more of these scales starting to pop up where we haven't seen those in the past, and new applications are coming for those. Also, we're seeing more of those now also in wastewater applications that are utilizing reverse osmosis systems. Beerstone, very interesting one, primarily in the ethanol process side of their business, not in the cooling or boiler, but rather on the process. Has many constituents, but primarily calcium oxalate and magnesium phosphate are the keys. It can also have organic zinc and other minor components can be present, but a very, very concern for the ethanol industry in their process, the formation of beerstone. It's another one that I find very interesting, low and no phosphate programs. I'm starting to see an increase in the governments requiring folks to eliminate or reduce the amount of phosphate that they have in their discharge. The cleaner industry, detergent industry was hit very hardly over the last few years in that area. There's no reason to believe that maybe the water treatment industry eventually wouldn't fall into that focus also. We're seeing restrictions on the Chesapeake Bay, the Great Lakes, certain Carolina rivers that empty into the Atlantic Ocean, and the U.S. West Coast. So it's really becoming a big challenge. The programs are being programs on the market right now are very effective controlling scale. However, corrosion control is now still remaining a challenge. If you remember the situation in Toledo with the algae in Toledo, very, very much like what's going on there, where although obviously they've traced it back totally to phosphate, but phosphates can enhance algae growth. This is just a map here showing where we're seeing phosphate restrictions. Again, California and the West Coast, the Great Lakes for a number of years, the Chesapeake Bay also, and then a few rivers, not a few, but several rivers in the Carolinas that discharge out into the Atlantic Ocean. Also starting to see a number of requirements for higher temperatures, specifically in geothermal evaporators and process. Typically when water treaters are designing programs, they're looking at what they call the skin temperature inside of heat exchangers. And typically that skin temperature can be anywhere from 120 to 140. However, in geothermal and evaporators and in some processes, we're well into the 200s and higher as far as water temperature. So programs are being developed to control higher temperature applications. And one more is reverse osmosis. We're starting to see much more reverse osmosis, quite a bit along the Florida coastline as the ocean starts to impinge on many of the wells. In the RO market, we're seeing needs for NSF certification and then also manufacturer certifications for these products on their membranes. So some of the personal observations I've made in the market over the years, there are numerous options available to everyone for controlling a variety of different scales. It's one of the things I've seen most in the market is we're seeing more and more and more new chemistries come on board. We're seeing more and more options and ways of going about treating systems. Regional chemistries must be considered and concerned with and taking a look at when designing a program. Product and treatment experience really boils down to what you feel most comfortable with when you're treating a system, understanding the pros and cons of the product or products, understanding what the limits are, and really understanding how best to treat a program based on the chemistry that you have and the experience you have. And then how easy it is to control the products you're currently putting in. Is the program difficult to control? Does it get out of control very easily? That's also something very much to consider. More and more and more, we're seeing need for certifications, NSF, FDA, CFIA being a Canadian certification. Again, this was an area that always surprised me, was many water treaters are also interested in cleaners. So it's something that when making calls and talking with folks, there's also an interest in these products being used for cleaners. Kind of going back to number 3 here, personal choice. What do you feel the most comfortable with? Which chemistries do you feel the most comfortable with, understanding how they work? Another key thing is availability. How readily available are these building blocks for the components that you're putting together? Are they easy to get? Or are they difficult to get? And then lastly, what technical support is needed to really provide good support to your customers and understanding really what is the best program for a particular system. That really concludes my presentation for today. I very much appreciate your time and being here with us today. This is my contact information. If anybody would like to write it down, available either through the email or through either one of the phones, either the cell or the office. Cell's usually the best first choice because I do travel quite a bit. But Brian, with that, I've completed. Are there any questions? Excuse me, any questions that may have come up?
Yes. Some people have typed in some questions here during the presentation. We'll go through a few of them here. Let's see here. One question is, can you give me an example? Can you give me an example of regional water differences?
Yeah, I realize I normally do talk about this one. One of the things that I've seen is, as you all know, as Brian had mentioned, I live in Pittsburgh. Been here all my life, and one of biggest challenges I found getting into this industry was realizing that there are waters that are different throughout the country and the world, frankly, than what I've experienced here in Pittsburgh. In Pittsburgh, we have a fairly, I would say, medium to low hardness water. Very, very easy to treat and very easy to control. Years ago, I was visiting family in Midland, Texas. That's when I was with Calgon, and my aunt asked me, they were having problems with their little RO unit under their sink, and could I take a look at it? And to be frank with you, back in those days, I didn't know what an RO unit was, but they knew I was a water treater, so they said, can you give us some help? So I took a sample of their water and put a fictitious name on it and sent it into Calgon, who did an analysis for me. And when I got it back, I was dumbfounded. I mean, it was looked better than some of the boiler blow, or worse than some of the boiler blowdowns that I'd had in my system. So it really opened my eyes to really start understanding the difference in the water treatment in the regions. Down in the Texas area, West Texas, Midland, very, very, very high hardness, high alkalinity, high silica. And so some of the regions and just some of the notice that I've seen over the country, how varied the water can be and how much you need to really realize regional applications and not just have a one product fits all type system or water. I hope that answers it.
Okay, thanks. Another question is, let's see here. How do I determine which product or products are best for my application?
The way I always answer this question is, it really boils down to a water analysis. I'm really understanding what the water chemistry is and what you're trying to accomplish. Too often I get calls with, I have a scale problem, what do I do to replace or to prevent it? With really not knowing, number one, what the scale is or what the water conditions are. So by far the best way of doing any kind of recommendation, ideally what you like to have, if there is a deposit or scale forming, you like to have a sample of the deposit and a sample of the water that's creating that deposit. And then once you have that, you can make a determination on really what chemistries or chemistries make the best choice for preventing or controlling that scale. I should also mention not only water, but also understanding the system. What are the temperatures? What is the system? Is it an evaporator? Is it a cooling tower? Is it a spray system? But those are really the key. And I would go back to water chemistry being probably the most important. Okay?
Thank you. Next question is, can you explain LSI and calcite?
Yes. Should have probably put this in the presentation a little more. What LSI is, it's a formulation that was developed many, many years ago, Langmuir Saturation Index. It takes temperature, hardness, calcium hardness, total alkalinity, pH, and total dissolved solids, and generates a number to indicate whether a water is scale forming or corrosive. And it gives you basically a feel for if you take this water and have those, 5 or 6 factors, can tell you whether or not you should experience scale or corrosion. And again, that was developed, I've been in this water market now 36 years, and I heard about it back 36 years ago. I don't know the exact date, but it's been around for many, many years. What calcite saturation is it takes a look at many more components. In this case, LSI looks at 5 or 6, whereas calcite saturation really looks at the ability for calcium to bond with other ions in the water, phosphates, sulfates, barium, whatever the case may be, and other components and how they come together, and gives you a better indication on the scale formation of water. You'll hear calcite will be read as a number between 1 and 300 or even higher. Anything over 1 means that water could scale. The higher you go in numbers, the more apt it is to scale. But it will also give you a better understanding of what potential scales can come out, not just calcium carbonate in the case of LSI. I personally am a big calcite saturation. That's primarily where my background is at and what I use for looking at predictions on water treatment. By the
Okay.
way, well, I'll just make one comment. You can get a really cool little app for your phone, LSI saturation, for like 99 cents. I use that periodically, but not to put a plug in, but it is available. There is an app for LSI saturations.
Great. Thanks, Kevin. Last question I've got here is, I hear the questioner writes, I hear the term acid form, quote unquote. What does that mean?
I'm perceiving that is in the form when you're talking polyacrylates, PAAs. When PAAs are manufactured, they're typically manufactured and they come out at a pH of around, I'm going to say 2 to 2.5, maybe as high as 3. I don't have a manufacturing background, but primarily when they manufacture a PAA and they don't do any neutralization or anything to it, it's come out in an acid pH, typically around, again, 2 to 3, 2 to 2.5. That's called the acid form. And what they'll do is they'll neutralize it with caustic and bring it up to maybe 5 or 6, say 4 to 5, 4 to 6, which would be considered partially neutralized, or bring it up to a pH of 7, which is fully neutralized. And that was done primarily to assist when folks were making formulations of products. If the product needed to have a low acidity or a low pH, they would typically buy the acid form. A higher pH, they would buy the neutralized form. I believe that's what the participant was referring to. But acid form, when I hear that, means a polyacrylate that has not been neutralized or partially neutralized. All right?
Okay, thanks. Let me just see if there's any other questions that have popped up while we were answering those. Let's see here. Yes. One person wants to know if the presentation is going to be available to review later on, and the answer is absolutely. Upon request, if you email Kevin or give him a call, then he will email a PDF version of the presentation. And I think that's about it. Great questions. Kevin, any further comments?
No, I very much appreciate the time. Any additional questions that we didn't get to, I will get to via email and get back with everyone. And again, if you would like a copy of the presentation in PDF form, please feel free to email me there and email me at this address, and we'll get it off to you shortly. So,
great.
Yeah, thank you.
So we were under a bit of a time constraint, and it looks like there were a couple of more questions that popped up. But we only have 45 minutes, so I think what we'll do is we'll address those questions offline. And for those who asked those questions here in the last couple of minutes, I apologize for not being able to broadcast those, but we will get some answers for you. And we appreciate the participation and look for invites to future webinars. And like we said at the beginning, feel free to offer some feedback on some topics that you'd like to hear from us on and learn more about. And with that, I thank everybody for your attention, and this webinar is now concluded.
Thank you very much.